Great. Okay. So, are there any questions from yesterday?
No,
Go ahead. Did someone say no? Okay, I assume so. Okay, no questions. Well, we're going to just briefly review what we talked about yesterday, and then we're going to start our sort of next topic, which is, for the people who are seeing this for the first time, might be a bit difficult. It takes some time just to sort of get your head around it, but it's really a language that you'll learn and become very familiar with pretty quickly. So yesterday we found that this graph, that this thing, e to the x, is a very fundamental shape in nature, and it looks like this, right? And this point, can someone tell me what that is? Let's see here. Small class, so I can, let's see, Alexis, can you tell me what that point is? The y-intercept. Okay, Matthew has stepped in and he said 0, 1. That's very good, very good. And the rest of the points are very easy to find. And you can literally just put it in here and you would find that this is 1e, that this is negative 1 over e, so on and so forth. And this is sort of the most fundamental exponential graph. And I said yesterday that you all should be very familiar with plotting, and using transformations to plot similar graphs. Okay, someone said something. Okay, I'm gonna mute everyone just in case. I think that might be distracting to some people. Yes. Okay. So if you need to say something, just unmute yourself. Okay. Okay. So yeah. So we're going to get. This is really just the beginning of this lecture. I want to just do this one example to sort of give you a sneak peek for what's coming next week. So this is y equals e to the x. Now, what happens if I just added a minus sign to the x here? How would things change? Well, I think some people might know the answer, but for people who don't know the answer, let's make two tables. So I'm going to use green for this first one, okay? For this table, and so we already have kind of what we need for a table. I'll use -2, 1 over e squared, -1, 1 over e, 0, 1, 1 e, 2 e squared. Okay, and that gave us that table. And I'm going to use blue for this new plot, and I'll do them side by side so we can sort of compare what's going on. So this is e to the negative x, and this was e to the x. So e to the negative x. So I'm going to put in the same points. Okay, and what would y be when x is -2? Let's see here. Wow, there's some unfamiliar names here. That's kind of nice. Let's see. Kennedy, are you there? Kennedy, what do you think y would be when x is -2? No response. Leanne, I heard from you earlier. What is y? What is y here? Look, I'm just asking you to plug in a point. So put in x is -2.
Is this e to the second?
E squared, very good. While you're at it, can you tell me what this one is?
1 over e.
When I put in -1 here, I get e to the -1, which is just e to the 1, which is just e. So it's positive e.
Okay.
Okay.
And then 0, I think it's just 0.
What is anything raised to the 0 power? We talked about this.
Oh, 1.
So this is 1. And then the rest is pretty easy. You put in 1 here and you get 1 over e, e to the -1 or 1 over e, and then this is e squared. So now, okay, thanks a lot. Leanne, thanks for participating. Okay, now I want, let's see, who's someone I haven't heard from? Monica, I don't think I've heard from you in a while. Can you compare this graph, or sorry, not this graph, this table to this table? How are they similar? How are they different? Okay, no signs of life. Let's see. Who else have I? Is it
Her
Kaji?
mic isn't working.
Okay, her mic is not working. Okay, no worries. Can someone else compare these two tables? I'm just trying to get, I want people to participate and not be bored or shy. So I'm trying to call it. But anyone, what's similar? The x columns are the same, right? But what about the y columns? Look, the column that was, or the entry that was mapped with -2, where is that now mapped? To 2. The column that was mapped to -1, sorry, I keep saying the column, the entry that was mapped to -1, which is E, now E is mapped to +1. The entry that was mapped to 0, well, that one stayed the same, but that's the only thing that stayed the same, right?
Reflector across the y-axis.
Yeah, so you can see that if I were to sort of draw lines of what happened to our y values, well, they got, all the y values that were assigned to previously negative numbers, they got now assigned, the same y values got assigned to positive x values. And all the, so basically, I'll just draw these sets of arrows and you'll sort of see the pattern here. So nothing, this is the only entry where nothing changed. And in a sense, this is our axis of I guess it's a tabulature reflection. It's the adjective describing a table. This is not a graph, this is a table, but you can see that the y values were reflected across this entry. And so graphically, if we were to plot this entire thing, I know you probably can't see this. I'll plot it out here using the table entries. So -2, e squared, that's way up here, -1, e, that's somewhere here, 0, 1, that's here, and then they die off, right? 1 over e and 1 over e squared, those are really small numbers. Okay, so now I'm going to ask you to compare this graph. Okay, you know what? I'll just replot, I'll sketch e to the -x in blue here. You can see that it's the same thing as e to the x, e to the positive x. So this is e to the -x. It's the same thing as e to the positive x, but everything is reflected across this line. And the only point that they share is this point right there. So this is a general result for graphing functions. So say I have the function y is f of x, and say it looks like that. Well, then it turns out y of f of -x, it's just reflected, it's just this entire thing reflected. Okay, this is kind of hard to draw now, but it would be the same thing. That's not quite how I drew it, but just reflected across the y-axis. Does that make sense? So we're going to talk about this generally, but whenever you have, so it can be anything. You can have, y is x squared, right? Well, this is a boring case because, okay, take x cubed, right? We said that this looks like this. Well, then if I put a negative sign on the x, this flips the entire thing across the y-axis. And it gives you this. So this is a general result, and we use the exponential to show that this is true. This is, again, not a proof. This is a graphical sort of explanation as to what's going on. But we said, oh, look, the y values are swapped. So the ones that were assigned to the negative x values are now assigned to the positive x values, and the ones that are assigned to the positive x values are now assigned to the negative x values. And that's exactly the definition of like reflection, right? So these are very important graphs. So one more time, I'll draw this. These are very important because this one in the green is called exponential growth. And this one is called exponential decay. So I'm sure these terms are familiar. There are so many examples in nature. I mean, nature is constructed with, the more you study sort of the physical world, you'll realize that nature is very well described by exponentials and sort of things related to exponentials. We'll talk about that more at the end of, well, maybe we'll talk about it tomorrow slightly. I don't want to get too into that yet. But like population growth, like we talked about the virus, the virus and human populations and animal populations, they all grow exponentially. That's just the way populations are. The economy can be modeled like interest, compound interest is exponential. Nature has so many examples. It's pretty amazing. If you look at a hydrogen atom and you, actually, okay, that's not a good example. It's more sophisticated than that. Yeah, they're everywhere. Radioactive decay, for example, can be modeled by e to the negative x. So you start with some mass of uranium or something, or some radioactive chemical, and over time, this is sort of how the mass evolves. Okay, anyway, all this to say that these are very important, and we came out with this nice result that when you put a minus sign on the x, that your graph gets reflected across the y-axis. Any questions? I assume not. Okay. Okay, I have a cool demo for you all, and I mentioned this yesterday. And on the quiz, there was a question that asked, okay, I'm not going to write the question. I'll just say, it asked, what grows faster, quintic polynomials or exponentials? And this is actually a more sophisticated problem than I thought when I wrote it to you. But the answer was that exponentials grow faster than quintic polynomials. So what are quintic polynomials? Those are the things that have the highest degree x to the fifth. And exponentials are things like e to the x or whatever. Generally, exponentials always grow faster than quintic polynomials. And to show this, I am going to share my screen. Okay, so I'm going to stop sharing this screen, but I'm going to start sharing. Let's see here. Okay, you're going to see the quiz for a second here. Okay, give me just a sec, people. Okay. No. Okay, so does everyone see this graph?
Yes.
Okay, great, thanks. So this is a line, this thing in the blue. This is a line. This is e to the x, this thing in the red, that's e to the x. And here, obviously, what is growing faster? E to the x, right? Look, as you go to positive, x values here, this thing is definitely winning in the race of which one is growing faster. In a sense, this is a steeper mountain than this. But now what happens? Okay, so x is kind of the simplest polynomial. Actually, really, the simplest polynomial is a constant. So this is really the simplest polynomial. But anyway, that's even more boring. If we were to go to a more sophisticated polynomial, like x squared, which is now shown in the green, what is growing faster? Let's see here. Jonadab, what is growing faster?
The green one?
Yes, thanks for stepping in. Wait, you said the green one is growing faster, but look. Don't worry about this side of the graph. I'm talking, when I say growing, I mean approaching positive x values. And here, look, the exponential is winning because the exponential is always above the green graph, right? The red graph is always above the green graph consistently. And in fact, that separation grows as we go up. See how much higher this is than like way down here? So what is growing faster? The exponential is growing faster. But what if you say, oh, well, that's just x squared. You haven't tried like higher degree polynomials like x cubed and x to the fourth. Okay, I'm going to put in x cubed. And look, right here, the exponential is winning, right? The right graph is above the green graph. But now look what happens. They cross, and now who's winning? Well, the green graph is above the red graph. And it turns out, if you keep going, they cross again. And I will keep going because to me, this is very amusing that they cross again. And look who's winning now. Does everyone see that the red graph is now beating the green graph? See how every point on the red graph is above every point on the green graph? How? That is a very good question. This is the nature of exponentials. They beat they beat all polynomials. And in fact, I'm going to do x to the fourth. And then I'm going to, you will not believe, okay, so here's x to the fourth. Look how steep, okay, I'm gonna go back down to the axis so you can see look how steep this polynomial is. See how it grazes 0 and then it really shoots up. So in this vicinity, the exponential is beating the green graph, but very quickly, just around 1.5, a little bit before 1.5, they cross and the green one starts beating the exponential. And if you stopped here, you would say, oh, the green one always beats the exponential. But as was the case in x cubed, if you keep going, and you can see how much I went to 10,000 here. When you get to around 10,000, a little bit before 10,000, the exponential starts winning again. So there is a range where the polynomial beats the exponential, but in the long run, the exponential always beats the polynomial. Pretty cool, right? So Long has sent a graphic. I encourage people to communicate about those things, like maybe before or after the class. But right now, let's keep chugging along with the lecture. Okay, so I'm gonna stop this sharing back to the whiteboard. Okay, so the right answer to that question. So many people missed it, but I want to make sure people are like in good faith, with this idea that exponentials grow faster. Okay, so that was sort of a long demo, but to me, this is an amazing result. And for the seniors, this will make more sense to you. But it turns out, well, I don't know, this might not make sense to you. But so this is a result from calculus that exponentials can be written as the sum of polynomials, as an infinite sum of polynomials. So it's amazing to me that exponentials can grow faster than polynomials when exponentials are just the sum of polynomials. And in calculus, you'll find, so again, this is not on the SAT, but for the seniors who are taking calculus, and I think BC calculus will cover this, it turns out that exponentials, like e to the x, for example, can be written as a sum of polynomials. And that sum goes like this. And I'll kind of explain what's going on here. And you can see the pattern. So the degree increases by 1, and these exclamation marks in the denominator are the factorial, which is just a convenient way of describing. So 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, 4 factorial is 4 times 3 times 2 times 1. So these numbers in the denominator get increasingly large, which makes the contributions of these higher order terms become increasingly negligible. But if you keep going, if you go on and on and on to infinity, you'll approach this exponential. In the limit that you go to infinity, this entire sum is equal to this exponential. So to me, it's amazing that all exponentials grow faster than polynomials, as we just kind of graphically showed, when in reality, exponentials are just the sum of polynomials. And it's not like a crazy sum, it's not like these terms are dominating. Certainly these few first terms are dominating, right? Because 1 is much bigger than like something over 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. That's a pretty small number, right? So anyway, okay, that's really an aside. Okay, so the sort of topic of today's lecture is reformulating this notion of exponentials. Okay, and people are messaging. Okay, so Robin said, okay, I'm not sure if you're addressing what I just said or Long's like animation, which I will watch when the lecture's over. If you have any questions, please just shout out, okay? So we're used to this form. This is our first formulation of the exponential. And I've written it symbolically, generally, that a to the power of b is c. So a, b, and c here could be any numbers that satisfy that relationship. Like here, a is 2, b is 2, c is 4. Or a is 2, b is 3, c is 8. So on and so forth, but this is a general description of exponentials. And it turns out that there is an alternate formulation that is sometimes more convenient than this formulation. And that alternate formulation expresses the same amount of information as this first formulation, but it can help us do problems. And that alternate formulation is called the logarithm, or the logarithmic form. And it's denoted by this symbol. It's really a symbol. It looks like the word log, and that's how you would say it, log, but it's a symbol. Okay, so it's a transcendental thing. Just as our notion of exponent is, right? That this is a transcendental thing. Remember when I gave you the example of the high school kid who he had this sort of thing to solve, and he said divide by sign, right? And how ridiculous that is, because you can't, sign is a symbol. Sign is not like a number or a variable, right? So similarly here, log, so if say I have, log of x is 10 or something, you can't divide by log. This is not the meaning of log. Log is not a number. Log is a symbol, it's an operation. It describes what you do to x, okay? So this is not a number, this is an operation. And specifically, the logarithm is defined in terms of the exponential. So for the exponential a to the b equals c, the equivalent logarithmic form, it takes the base, okay, so now colors are going to be very useful here. It takes the base a, and it puts that down here. And it makes sense because this is called the base of the logarithm, this little index here. And it makes sense that it's the base, right? Because it's the lowest thing in this entire, you look at this thing and this is sort of in the basement, right? So the base goes in the basement. I don't know, that's corny, but just a way to remember. Okay, so the base gets put here. The answer to the exponential, in other, like the right-hand side, so the thing that the exponential equals, that gets put here in the parentheses of the log. So this is what the log eats, so to speak. This is what you feed the log, right? And what does the log, oh, sorry, I should have used a different color. Let me do that. Here. This is what the log eats, okay? And what does the log spit out? The log spits out the exponent, b, the exponent on a. So this is sort of the tricky part of today's lecture. For people who haven't seen this before, I know how much this is going to mess with you because it messed with me for a long time when I learned this. So you have to become familiar with this, and we're going to use some examples in translating. So being able to go from form 1 to form 2 is very important. So write this down. This is like sort of the crux of today's lecture. If you're unfamiliar with this, please write this down. Okay, so the only way to get good at doing this conversion is to do it, just like anything in life, okay? So we're going to write the following exponential statements as logarithmic statements. So bear in mind, there is an equal amount of information expressed in statement 1 and statement 2. There is nothing special about either one of these statements. They're on the same footing, but note that the right-hand side of a logarithmic statement gives you the exponent, right? The right-hand side of an exponential statement just gives you the answer to that exponent. So they're sort of, the answer, so to speak, is a different thing, but they contain the same amount of information about A, B, and C. So we're going to write some things as logs just to get practice. And what here is the base? Let's see, I'm going to call, this is a perfect opportunity to call. Let's see, Fiona, you're the first name I see on the list. Fiona, what is the base here?
It's a
2.
2.
Oh yeah.
It's okay. Okay, I'm calling on people with the hopes of making people participate. But the base is 2. Very good. So base. What is the exponent here? Someone else. Isaac.
3.
Okay,
Sorry.
great. Okay, no worries. Okay, I'm calling on people, but I appreciate anyone participating. Okay, this is the exponent. And now what is the sort of the right-hand side? Well, that's obvious. It's the only thing that's left. Okay, so now how does this all fit in? Okay, so these colors might not match what I originally had here. So sorry. But in our logarithmic formulation, I would write log, and remember the base goes in the basement of the log. This is the basement, right? The lowest spot. Log 2, so look, the base. What does the log spit out? Well, the log spits out the exponent. And what does the log eat? The log eats the right-hand side of the exponential form, and that's 8. So I should have really used colors here, but I think you all can see sort of what's going on. So does this make sense, how I got from here to here? This is just notation, and it's really all about getting familiar with rewriting the notation. Okay, let's do another. So what here, okay, I'm gonna call on someone else. What is the base? Let's see, anyone, let's see, I haven't heard from Robin in a while. Okay, Nishan has already jumped to it, and he said the base is 3, very good. Base. So I'm gonna immediately start writing what the log is. So the base goes in the basement, 3. What does the log eat?
27.
27.
It eats 27. Good. And what does it spit out? It spits out the exponent, which is 3. So here there's some degeneracy, so to speak, between the exponent and the base, but that's just coincidental. Okay, how about, okay, does this make sense? I'm sort of starting to go a little bit faster, but I just want people to get familiar. Let's see. Okay. The base, well, that's 4. So I'm going to write immediately log base 4. The 4 goes in the basement. The base goes in the basement. Well, the log eats the 16, and it spits out 2, the exponent. So the log always spits out the exponent. So in a sense, a logarithm isn't, like when people say a logarithm is an exponent, that's not really true. Again, the logarithm is not a number. The log itself, is an operation. It's a thing that you do to a number. But yes, if you think of it as a machine, the log as a machine, the thing that it spits out is the exponent. The thing that it eats is the right-hand side. The thing of the exponential thing. I don't know what to call that. I'm sure there's a mathematical word for this number. Anyway, I hope this is becoming increasingly intuitive. The base here is what? Let's see, I'm going to call on someone else I haven't heard from. I was going to call on Robin. But anyone, let's see if Robin is not there. I have not heard from Tanisha in a while. I've not heard from Thomas in a while. I have still, go ahead. Sorry, say it again.
Base is 5.
The base is 5. Very good. So the base, again, I'm just going to immediately write the logarithm. The base goes in the basement. What does the logarithm spit out? Is it this or this? Negative 3.
125.
That is not what it spits out. The logarithm spits out the exponent. And what is the exponent?
-3.
Yeah, so that's in a sense what the log equals. I am hesitant to say that. It's what the log spits out, right? And what does the log eat? That's what you said earlier. The log eats the right-hand side, right? Okay, so is this making sense? So right now we're not doing any computations. We're just taking exponential statements and writing them in terms of logs. So there's no math here. We're not doing any math. We're just getting familiar with the notation. Let's do one more, just so people are familiar. So let's see, someone else, maybe 2 more. Let's see, Thomas, I have not heard from you. John Perry, I have not heard from you once the entire course. Solina, I have not heard from you in a while. Look, literally anyone, but I do want to hear. Monica, I don't think I've heard from you in a while. Mauricio, I haven't heard from you.
Log base 2 of 1/32 equals -5.
Awesome. That is exactly correct. And you said it all at once, so thanks. You saved me the pain of going through. Okay, it's not a pain. Okay, what happened here? Sorry, my screen just zoomed up. It's not a pain for me. It's just, I don't know how slow I should be going, but yes, this is very correct. So the way you did that was you took the base, that went in the basement. The -5 is what the log spits out, and the right-hand side of the exponent is what the log eats. Okay, one more example. How would I express this statement? So this is different from the other statements. This is a little less clear. How would I express this as a log? Well, the first step is to convert the radical here to an exponent. And how would I do that? What does taking the square root mean in terms of exponent? Yep. So this is the same thing as ABCD to the power of 1/2, and that equals F. Okay. Now, how would I write this? Now we have our nice old form of log base, I don't know which letters I used earlier, but this was the form of our log. And so I'm using different letters here than I used earlier. But see how this is in this form? ABCD to the 1/2 is F. Well, here's our ABCD. Sorry, the letters are the same, but this is our A here. The 1/2 is our C, and the right-hand side is our B. So now can someone immediately tell me what the logarithmic form is of this thing?
Log of ABCD
So that the entire thing is our base.
of F
Very good.
equals 1/2.
Very good. Yeah, so this is our entire, so it looks kind of funny because our base is this big ABCD nonsense, but this is the exact way you would write this as a logarithm. And it's kind of nice, Go ahead.
Does your base always have to be in parentheses, or did you just write it in parentheses since it was like that originally?
I wrote it in parentheses so it's not confusing, but it's a very good question. It does not have to be in parentheses. In fact, rarely is it in parentheses. I could have just written ABCD, but I didn't want to confuse people, with, what is, what's the base and what's the argument? What's this? I didn't want to confuse it with F. So anyway, you do not have to write it in parentheses.
Okay.
Good question. Okay, anything else? Any questions about how we did this? So this is a bit more abstract, but it's leading us in the direction we want. Because now we're going to compute logarithms. And so earlier we were just given exponential statements and we converted them to logarithms. Now we're going to take a logarithmic statement and in our heads just figure out what this equals. And I think the best way to do this, people who have experience with logs are going to immediately know the answer. But the best way to do this initially is to convert the problem to an exponential problem. So in a sense, we're going to be going the other way. Earlier, we were going from exponents to logs. Now we're going from logs to exponents. And then answering the exponential problem will give you the answer to the log problem. So this I'll do the first one kind of for you. This written as an exponent. Well, for the ease of notation, I'm going to call the answer, I'm going to call it A, okay? Just some arbitrary letter. This is A, this is a number. And if I were to write this entire statement then as as an exponent, we're given a log, we're trying to write it as an exponent. Well, this would be, my base is 2. My exponent is what the log spits out, that's A. And my right-hand side of the exponent is what the log eats. And now I just need to cook up a number. I need to ponder. I need to think about a number, A, that satisfies this equation. And it's not very hard to do. You can try 1, you can try 2. And it turns out if you try 3, that indeed 2 cubed is 8. So A is 3, and that's the answer to the problem. So that's sort of the approach we're taking. Okay, I hope that wasn't too fast for anyone. So basically, what did I do? I converted the problem to an exponential problem. And I said that this is 2. So I called the entire right-hand side, this entire thing, I called it A. And then I rewrote the problem in terms of A, and then I guessed a number, right? I picked a number A that satisfies this equation. And that number is 3. So the log base 2 of 8, that's how you would say it, log base 2 of 8 is 3. In other countries, people say it differently. Some people will say like log of 8 base 2. But to me, that's a bit confusing because you read left to right. At least we read English left to right. So anyway, okay, I hope this makes sense. Let's do a few more. Okay, so how would I find the right-hand side? How would I find the answer to this log? Again, I'm gonna follow the exact same steps. So I'm gonna call the right-hand side A, some number A, and the base is 2. So now I'm gonna write it as an exponential. So 2, well, the log spits out the exponent. So 2 to the A, And the log eats the right-hand side of the exponential. So 2 to the a is 16. And here again, you can pick numbers. You can try a as 1, you can try a as 2, a as 3. None of these will work. So you can try a is 0, a is -1, a is -2. I'm literally just guessing numbers, and it turns out that when a is -4, that this is a true statement. In other words, 2 to the -4 is 1/16. And how do I know that? Well, I know that from what we talked about last time, that this is really just, sorry, not e, that this is 2 to the 4th to the -1, and 2 to the 4th is 16. When you have this -1 out there, then you just take the reciprocal of that. So it gives you 1/16. So the answer to this problem is -4. Okay, does this make sense? I'm going a little bit faster because I don't want to bore our older students. Let's do another example. Shout, just you don't even have to be polite. Just let me know if people are confused. Okay, so yeah, I haven't been looking at the chat, but I'm assuming, yes, people are getting these.
-3.
Yeah, so -3, very good. So yeah, thanks for participating, because I really have, yes. So someone immediately said -3, and the way she did that was she probably in her mind said, okay, well, this converts to the statement. If she didn't know what this was, she called this a. This converts to the statement 3 to the a is 1/27th. And then she said, okay, well, what can a be to give me 1/27th? And -3 is the answer, because 3 to the -3rd, well, that's just 1 over 3 times 3 times 3, and that's 1 over 27. Great, good job. Let's do one more. A bit harder, but really the same thing. So can anyone just tell me the answer here? Four. Okay, 4 is not correct. -4. Yes, the answer is -4. Okay, how would we do this? So I'm gonna call the right hand side a, and then I'm gonna rewrite this as an exponential. So 10 to the a is 1/10,000th, and I can write 1/10,000th as 10,000 to the -1, and I can also write 10,000 as 10 to the 4, right? So this is just 10 to the 4 to the -1. And we know that when you have this configuration, we talked about this all day yesterday, that this is just 10 to the -4. And look, 10 to the a is equal to 10 to the -4. Therefore, a is -4. I hope this is making sense to people. Okay, good. Okay. How about this? A bit more abstract, but I'm going to use the same approach. First of all, can anyone tell me what the answer is? Any of the more experienced people? Anyone?
-3.
Very good. Okay, so whoever has been, yes, I'm recognizing your voice. I don't know your name because I can't see you. But yes, you are very correct. This is -3. And so I'm just going to quickly do this the way I have been doing for people who want to see. So I'm going to call the right-hand side a, and then I'm going to rewrite this entire thing as an exponential. So here's my base, pi. Here's what the log spits out. That's the exponent. And here's what the log eats. That's the right-hand side of the exponential. And look, there's only one number that will satisfy this thing. To make the right-hand side and left-hand side match up, a is clearly equal to -3. And generally, we're actually about to see, in these last few minutes of the lecture, after just a few more examples, we're about to see that it's generally true that if you have like log base a of a to the n, that this is just n. So when the bases are the same and a is raised, and one of the this argument is raised to an exponent n, then the entire log is just equal to n. So we're coming to that general statement, but this is sort of this is a special case of what I just said. Okay, I think this might be the last computational example. Okay, maybe a few more. Okay, I'm going to do this faster. Oops, wow. Okay, I'm going to call the right-hand side a. I'm going to rewrite this as an exponential. That's 5 to the a is 625. Now I need to find a number a that satisfies this relationship. It might look hard, but I do know that, I know my perfect squares pretty well. And it turns out that 25 squared is 625. And you all know that 5 squared is 25. So I can write this entire thing as 5 squared squared. And 5 squared squared is just 5 to the 4th. And so this entire thing is 5 to the 4th. And the only way to make this statement match this statement is letting a equal 4. Right? See how a can only be 4 to make this statement true? Okay. Okay, this is just the same thing as that pi, you know, as the one that we just did to, it's very similar to this example. I've just used a different transcendental number here, a different irrational number, e. So immediately, if you were to follow that last example, you would say that this is 2. Yes. You would say that this is 2. If I wasn't familiar with that yet, I would write the right-hand side as a, or some, you can use any number. I'm using a because it's an easy letter. And then I would rewrite this in exponential form, and that would be e, here's my base, e, to the power of a is e squared. And clearly, you know, the only a that satisfies this equation is 2. You need the left-hand side to match the right-hand side in an equation, and letting a equals 2 does the job. Okay, so this last example is usually you would never see log base e. And the reason you would never see log base e is because e is so profound and so fundamental to nature that people have invented their own notation for e. And it's not drastically different, but yes, if you look in the chat, Aditya has written ln, or natural log. And that is exact. So this is denoted. So first, bear in mind, this is not a number. Are people familiar with this 3-bar equal sign? This just means, like, by definition. You'll see this more in more advanced courses. But yes, log base e of something in definition is called ln. And so whenever you see ln in your mind, you should think log base e. So if I were to write, it's nothing but notation. There's no new math here. But if I were to write this the sort of correct way, the way mathematicians would write this, I would write this as ln, or the natural log of e squared. And I think seniors will find themselves writing ln in their calculus class more than they'll be writing log, because in calculus, like I said last time, you know, the derivative of exponentials, like of e to the x, is itself. And so there are similar properties for the natural log that make it really nice and beautiful. So you'll be finding yourself writing the ln much more than you'll find yourself writing log base other things. Okay. But for the purpose of the SAT, this is just a notational thing. I just want you to know what it's about. Okay. Lastly, there are some special cases of logarithms, okay, that we should be familiar with. This one we already talked about. This we said is just b. So whenever you have the same, you have a base, and then you have that base raised to something in the argument of the log, well, that thing that it's raised to is what the log equals. Okay. And if you doubt me here, we're about to do some proofs, actually. They're not proofs, but they're sort of derivations of properties of logarithms. Here's another special case. Just as anything raised to the 0th power is 1, well, similarly, the equivalent logarithmic statement is that the log of 1 base anything, right? The log base anything of 1 is, can anyone tell me?
0.
0, yeah, that's exactly the same statement. So these statements are mathematically equivalent, but here I'm just expressing it differently. So whenever you see log of, it can be anything, you know, log of, the base can be anything. I don't know, pick your favorite number, f of 1. You should immediately, as soon as you see that the argument is 1, you should just write 0. Just as quickly as when you see anything raised to the 0, you write 1. this, the speed at which, the willingness with which you write the answer here should be equivalent. Okay, so those are special cases, but there are some properties that are very good to know. And so I know that today's lecture, what happened to, okay. Today's lecture is probably a lot for people who are new to logs, and I'm guessing most 9th and 10th graders are new to logs. So this might take some time to like internalize. But in these last few minutes, I'm just going to cover these properties. And the first property is the log of a product. So in all of our examples, we were taking like log of some number a, something of this form. But what if a can be expressed as two other numbers, like x times y, right? How then would I take the log of a product? How would I evaluate the log of a product? And so generally, I would like to find some way to write this. See, this is a product, x times y. And I'm going to figure out what this equals by calling. So this is a bit more mathematical, okay? This is almost like a derivation. So just hang with me here, okay? I'm going to call m. I'm going to call that log base a of x. So, and then I'm going to call n log base a of y. And equivalently, you would realize, from our entire discussion today, that I could write these statements respectively as a to the m is x and a to the n is y, right? And so, look, this is x, this is y. So now I'm going to put these back in here. X and y go back in here. So log base a. Now I'm putting in x. Well, x is a to the m. See, x, a to the m. Y is a to the n. But we know from our exponent properties that when the base is the same, what happens to the exponents? Well, we know that you add the exponents, right? I'm putting more parentheses than I need just to make this extra clear. Okay, well, this is all good, but we can simplify this, right? Because remember, from this property that we just talked about here, when the base is the same, this thing just comes out in front. So look, the base here is equal to this base, and so this entire thing is just m plus n. Just as log base pi of pi to the 2 or whatever is 2, it's just the exponent. Similarly here, look, I have a here, I have a here. So this entire log just equals the exponent. And what is m plus n? Well, look, here's m, and here's n. It's at the edge of the screen. So m plus n is just the sum of these logs. Log base a of x plus log base a of y. And so this is my final sort of statement. So to summarize, you don't need to memorize, you don't need to be able to do this proof. In fact, I would not, if you just asked me to do it, it would take some time to figure out how this all works. But it's sort of gymnastics. But what you should know off the top of your head is that the log of a product is the sum of the logs of each factor. So I'll say that again in words, and here it is in writing, in math. The log of a product is the sum of the logs of each factor. So this is the product. The factors are x and y. And the sum of the logs of each factor is log x plus log. Sorry, I wrote this wrong. I don't know where that came. It's log base a. Log base a of x plus log base a of y. So this is sort of, I think on the homework I called it property 1. I'm not sure though. These properties are summarized in the homework, but I haven't proven this for you in the homework. So I think this is property 1. I'm not sure what it is in the homework. Okay, the second thing to know, and it's very similar, we've sort of done the heavy lifting, but what is the log of a quotient? In other words, what if I had log base b, of a is c, and if a can be represented by x divided by y, or in other words, if a can be represented by two numbers divided by each other, well then I would like to find, it would be nice if I could find some way to express a generic log of a quotient. Okay, and I'm not even going to go through this for you because actually it's the same thing as property 1, but just realize I can write x divided by y is x times y to the negative 1, and then I can apply property 1. So first of all, do you agree that x divided by y is x times y to the negative 1? I hope you do,
Yes.
because we talked about how alpha to the negative 1 is 1 over alpha. So that's what's going on in this stage. And then I'm going to apply property 1 here. And by property 1, I'm literally just applying this. By property 1, this is log base a of x plus log base a of y to the negative 1. Well, I guess I haven't proven this yet. But log base a of y to the negative 1 okay. Maybe I should have gone through a rigorous proof, but this is equal to the difference. Okay, so the negative 1. So I should have done this. Okay, I should have. Okay, anyway, so the log of a quotient is the difference of the logs of each. So here it's more specific because you have a numerator denominator, but it's the log of the difference of the numerator, so the numerator minus denominator. So generally, I'll summarize property 2. Log base a of x divided by y is log base a of x minus log base a of y. And you see that this is the exact same as property 1. It just differs by a minus sign, right? Let me zoom out a tiny bit. So here's property 1, and here's property 2, and here there's a product and you have a plus sign. Here there's a quotient and you have a minus sign. Okay, I hope this is making sense. So what you want to write down, you don't have to write down this proof, so to speak, but you should write down these big properties. So write this down, write that down. Okay, we're almost done here. Log, this is what I should have shown first, actually, because I used this property in the proof and I couldn't justify myself. What is log base a of something raised to something? So x to the n, for example, right? What would this be? How would I evaluate this? And this is actually what I needed right here. I wish I had shown this proof first. So, okay, next time I teach this, if I ever teach this again, I'll do this property, what is going to be property 3, I'll do it first because I actually needed this here. In other words, what we're showing is that, in this case, log base a of y to the negative 1, that's just negative log base a to the a of y. In other words, the exponent comes down as a multiplicative thing in front of the log. And the way you would show this is actually very easy. I would do something similar as what I did in the first proof, and I would call m log base a, which, written in the exponential form is a to the m is x, right? Here's my base, a to the m is x. And this means, making the substitution back in here, this means that log base a of a to the m, right? That's what x is, a to the m. And all of this is raised to the n, right? Well, I know from our exponent properties that a to the m to the n is just a to the m times n. So this entire thing becomes a to the m n, where these are multiplied together. And I know from, our previous examples that when this number is equal to that number, that the log of this configuration is just the exponent. And what is m? Well, m is log base a of x. And so this entire thing becomes n times log base a of x. And so this is our final statement, and this means that, in summary, that when you have an exponent an exponent that is being raised, if you have, x to the n inside the argument of the log here, that the exponent can be taken out as a factor, multiplying the log without that exponent. So it's a nice property, okay? So this is the thing, this is like what I'll call property 3. It's what I should have shown first. But yes, write this down. Okay, and lastly, I know we're just about done, and there's a very short, the quiz today is like 2 or 3 questions. It's really short. It should take like no more than 3 minutes. Lastly, there's this property called the change of base property. And it says that if I have log base b, if I have log base b, and say I don't like this base a, say I want to use another base, so that maybe this base is like 10 or something, and say I wanted to use the base e, and this is actually something you would do often because we like e as a base. But generally, I can write this in terms of any base of my choosing and let that new base be c. And if I were to use that new base c, then this log base a of b becomes log base c of b, of this number, divided by log base c of a. So I'm starting sort of with the statement of the property. So this is property 4. And the proof. So for those of you who don't care for the proof, you don't have to, this is just what you have to memorize and sort of get through with. But for those of you who want to see the proof and who are interested by this, the way I would prove this is I would call x equal to log base a of b, and exponentially, I would write that as a to the x is b, right? It's the exponential form of this. And then substituting that into this statement of log base b, log base a of b, I would have, sorry, actually, not substituting. Okay. What I'll do is I'll actually take, you see the statement here? I'm going to take log base c of it. And so I'm going to take log base c of both sides here, log base c of b. But we know from property 3, right, this property, that this thing is just x times log base c of a, right? The exponent gets thrown out here. And solving now for x, we're done. X is, log base c of b divided by log base c of a. And that is what I promised you it would be. Log base c of b over log base c of a. Okay, so those were the properties. Sorry that it was a bit rushed at the end. I know we're out of time, so I'm going to send the chat. I'm going to send the quiz in the chat. The quiz is really easy. It doesn't cover any of these last properties. I didn't think that would be fair because I just introduced these things to you all. But it does cover the things we talked about earlier in the lecture. So basically just evaluating logs, and it's free response. So you have to type in your own answer, and it should tell you if you got it right or wrong. Okay, so does anyone have any questions? So the link is in the chat. Does anyone have questions about these properties? I know these properties are a bit abstract, but they're very important. So take your time with them. You can watch these derivations again. I'll upload this lecture online. Any questions?